So, hi Florian.
Hi.
Let's start out by talking a little bit about you, what role you're playing around async, and so forth. So, go ahead. You can give it.
I'm mainly using the whole async stack as a trainer and documenter, and I also have conversations on API design as being part of the async-std team, mainly responsible for some of the project management, some of the goal setting, and as such I often implement smaller examples, larger examples, and my background is in network programming, backend systems, so that's a natural fit where this whole async story fits in.
So you've been doing async trainings for a while, right?
Yes, since effectively 2015. So I've been training Rust since 1.03 was the first training.
Okay.
But that was mainly, there's 10, there's sync, it's interesting. It has behavior around threads, and then constantly evolving. So, yeah.
What do you think? So I have here, can you sketch out for me what you see as the async stack and how your project fits in? So I guess async-std is kind of this runtime layer, right? So this bottom layer that intermediates, well, that allows you to open sockets and do other kinds of things, as well as tracking what tasks are executing and providing a scheduler. What are the different components of async-std, I guess, from your view?
So async-std is mainly two things. It's, first of all, the API, which is a pretty straightforward port of what the Rust standard library has, except that everything that used to be sync is now async. That's an interesting exercise in figuring out what in the standard library is actually in subtle ways sync, or doing any kind of synchronous calls. And the other part is the reactor itself. The thing where async-std is quite interesting architecturally is that all the details on how the reactor is implemented are private. So you cannot hook into it. You cannot, for example, register your own things directly on the reactor. So
you say, what is a reactor? Let's go.
The reactor is the component that drives the that's the executor. The executor drives the execution of futures, and the reactor does react on any kind of network events. For example, if there's any kind of data coming in from the outside, and your kernel tells you, by the way, there's a number of bytes ready to read from the socket, you can start reacting on that.
So in simple terms, it's sort of what calls epoll, so to speak. What asks the kernel where data is ready. Okay. And the executor is kind of the threaded runtime, essentially. What's actually executing the socket, the tasks.
Or whatever strategy you choose.
Sure. And you were saying that the reactor is not sort of open to the users. Maybe I didn't quite follow what you were saying about that. Can you repeat that?
So all the internal workings of that reactor are private in the sense of you can run futures on it, but you cannot, for example, put any kind of additional primitives on it. For example, you couldn't, like for example, our TCP listener requires some access to that reactor internally to properly be implemented. You can't implement primitives like that yourself.
Okay. So things like the TCP provider are kind of linked to your reactor and not separable, you're saying. And is that sort of part of async-std, the way that the design of something to do with async I guess you were saying async-std, or is it something more intrinsic?
I mean, it comes with an advantage and a disadvantage. The disadvantage is you cannot modify what runs on the internals of async-std yourself. The advantage is you can always be sure that the only components that run on there are components provided by the library itself. So it's the classic problem of information hiding in IT. So if you hide the information, what the internals actually look like, that gives you, and if you constrain the ability to hook into those internals, it gives you a much smoother path of understanding what actually runs there, and much more privileges on actually changing it internally for example, portability reasons.
Okay. And
it's much the same as the standard library in Rust avoids being platform specific. So
that's one of the things I'm kind of wondering about is how much of an atomic unit these different runtimes are and or have to be, and how separable they could be. So for example, if it might be possible to have a TCP implementation that can be shared between, I don't know, Tokyo, async-std, Fuchsia, and different libraries, or if that doesn't make any sense at all. Well, TCP lives in the kernel, I guess, for the most part, so it just doesn't make a lot of sense. But basically, at what point in the layer these things become disentangled, or can be?
That's a good question. I mean, our TCP listener, for example, is a pretty specific one that is bound to our system. All the API of it may be less so. So you could find a common API that all TCP listeners would implement. And this is kind of where you see the split in async-std as well. You can actually compile async-std in the mode that removes all the runtime and just gives you the API. But that also means that all the specific types, like TCP listener, all the socket implementations, will also vanish along with it. So you can then only use the external interfaces.
Okay.
I'm not sure if you can. You can probably derive an implementation or at least an interface that would work with all of them. On the other hand, then you're probably in the area where certain kinds of optimizations on these types or certain kinds of behaviors of these types might work better with different kinds of execution reactor behavior.
So I think what you're saying is there things like this TCP listener or whatever, you could sort of treat them like any future or stream or some core interface, but they also have things that are specific to TCP, say, and you wouldn't be able to access that because right now there's no sort of standard trait by which you could access that extra information. Does that sound correct?
Yes.
Okay.
The main question is how much are applications actually interested in those specifics of those types? Most applications are interested in that's a readable and writable socket, or it's a readable and writable thing even. They don't actually care about it's a socket. And then can be compiled against any of these. It can basically be generic over what their network implementation actually is. That's a pretty common practice. If you're looking past Rust land, for example, in Java, everything is injected. How your application connects to the network is injected. And the thing that gets injected is actually a pretty concrete type.
Yes.
So I'm not even sure if a generic interface over TCP listener makes sense. I think a generic interface over this is how you connect makes much more sense.
So we're kind of, I'd like to turn our topic a little bit. We're kind of randomly in this corner of dependency injection, but I think that, although it seems pretty relevant, but I wanted to talk a little bit to you about specifically around, I guess, the larger strategy of stabilization and interop and traits. I think we've talked a lot about the futures crate, for example, and what role it ought to play, and I'd like to get your take on that. I think right now we have the futures. Now we have exactly one stable trait, right? Future. I think we probably want more, which is kind of what we were just discussing. And so I'm curious to hear your opinion either on how we should go about driving that or about which traits you think are most important and so forth.
Yeah, I think reading and writing is pretty important. that's what we mainly do. I think towards stabilization, the question is which levels of stabilization do we want to have? Stabilizing to the standard lib is always a pretty big chunk that needs a lot of, that doesn't give much room for failure, because once it's in the standard lib, we're stuck with it. On the other hand, there's the ability to actually move futures over to being a stable, or to move some parts of the futures interface over to being a stable place for libraries to implement upon on top of it, but not being a as rigid as the standard API. There might be a futures 2.0, there might be a futures 3.0, maybe not next year, but maybe in 2 years, maybe with a compatibility API. Those are all options that the standard library doesn't really give you. So I think having a co-library on top of the standard library types makes a lot of sense. So I'm not sure if reading and writing I would put into that category. I would actually putting them into the category of flagging them for inclusion in the standard lib. But there's tons of other things. A lot of the things, the stream API, some of the support macros, for example, some of util sounds like good for stabilization, or maybe not.
Right. So what makes the difference between the async read and async write and the stream API in your mind? Like, why did you say that one would go into the standard lib and one in the futures grid? Assuming we went this way.
Stream API mainly because this still talks about maybe having language support for it. So that might, so for example, a valid strategy would be having stream in the futures API first in a stable fashion until we have language support, and then maybe releasing a futures 2.0 in as a co-release to a potentially new language features, maybe shipping a new stream trait.
So one strategy I think we can do, if we take, let's just go with reality. Let's say we have like something very specific. We have the futures 0.3 release right now, right? Which I wish, or I don't think 0.3 sends a strong message of stability. And maybe we would have preferred if it's 1.0 or something. But ignoring this question, it contains a async read and async write trait definition, which might be suitable for the standard library. And let's say we decided it was. What we could do is bring it into the standard library and then essentially re-export it from 0.3, essentially issue a new minor version that re-exports the version from the standard library. At least I think I've heard this proposed. Although, yeah, I think that works. Just wondering now, does that work? I think it does because no two minor versions would coexist together. So the danger would be if you had, yeah, and that's, in any case, yeah, we could do this. And in theory, since it's the same trait, it's re-exported, it should sort of, should just work. And now, of course, you have full interoperability between stuff that was written against futures and is now, and newer stuff that's using standard, right? That seems like a pretty good, like the gold standard of what you're looking for. And I guess we could take a similar strategy, assuming we don't make changes, basically.
I mean, given that the library is still 0.3, we could always go say, pessimistically, this is 0.4. There might be changes that break on your particular library. I think the ecosystem moves fast towards stabilization, but it's not a binary thing from now everything's stable. I think it's more of a slowly getting off the experimental the experimental state. And this is also, I think it's reasonable to release futures as 0.3 because given the history of the library, you have it, basically it was the experimentation for even futures. Do futures even make sense? What would a good futures API be? Futures 0.1 was an extremely generic heavy API where every return type was generic and it was a good it was a good experiment on seeing how far you can go and whether that even makes sense or if you can make it simpler. So 0.1 was a very good experimental library and 0.2 in a similar way. So I don't know. And taking the parts out of 0.3 that are useful and then either putting them towards std and maybe releasing a smaller futures crate that assembles the things that are probably going to stay the same for the next year or
right. And the futures crate itself is actually composed of a lot of smaller crates already, right? I'm not sure.
Yes.
And I think that the idea is that if you're building libraries that should be reused, you're supposed to use these finer grained dependencies, mostly for several reasons, because that way maybe something in the join macro is redefined or something, but the async read and async write traits don't change, then your semver, if you just have a dependency on just that futures IO crate, that's kind of invisible to you.
Sure, and that also opens you up to, for example, giving different kinds of stability guarantees to parts of them, to different kinds of subcomponents. So it brings a lot of flexibility, and I think we should use that flexibility and decide. And this is what I mean by saying that it's not binary. We now split it into multiple smaller crates. So this gives us the opportunity about talking about smaller pieces of API and saying, okay, let's invest some time and focus on these pieces of API, and let's see if we can commit to them for the next, I don't know, time to come.
How?
I mean, that doesn't mean that we can't figure out at some point that we need to release a 2.0 plus a porting guide or tooling.
Yeah, I'm trying to figure out what it would mean if it's not in std. What does it mean to sort of, what does it mean? How do we make the decision to make it stable, and how do we communicate it, and how do we make it meaningful? Like, does it seem like an RFC is still appropriate, for example? I'm not exactly sure. I think the futures crate, I actually don't quite know. I'd like to find out exactly how development and decision-making has happened there. I think it's a little bit, I know there have been several people involved and so on, but it feels like we need to be able to signal this so that people can rely on it, right? And I'm not exactly sure how we signal that, apart from releasing a 1.0, and that begs the question, how do we decide to release a 1.0?
well, privilege of the responsible people for the crate. Whoever, however you might define this. I mean, there's certainly an amount of, but that's more, I think that's more project strategy. How we deal with these kinds of libraries and how we propose them and how we make sure that there's ecosystem adoption. And yeah, I like the Futures API. I must say, I always liked it in all of its experimental state. I mean, that was a lot of flux, but it has always been a very, very consistent API. Also, all the experimental states, like every time there was a larger change within the Futures Crates API, it was always consistently, it changed consistently across all APIs. That made it sometimes a bit annoying if just before a training you would have to update all of your examples, but once you figured out how the new API works, at least you didn't end up in a situation where you would have to say, oh, by the way, this training is happening in between two states. So this half of the example works that way and the other half works this way, which I think is an indicator for quality for experimental stuff. And that, in my opinion, has also been one of the things that Rust has always done well, in the sense of if there was a new strategy, you would completely, for example, when the standard library was still in that state, the standard library was either in state strategy A or it was in state strategy B. I think the question is, how many of those APIs do we want to keep in this level of quality, or how many do we want to put into it's now time to build your applications on top of it? Because I think that's the big problem that we currently have. People want to start building applications on it, and people have been writing applications on top of Futures, and we need to figure out where the places are where we can still iterate and where we're basically just introducing ecosystem friction. I think that's the big question we have to ask.
Oh, okay. What do you think the answer is? Or do you have an answer in mind? Or to put a slightly different version, if we were going to concentrate our energy on one thing or two things in the next 3 to 6 months, what do you think they should be? We being the Rust org here.
I think async read, async write, and streams. The streams are important in the sense of, I think they're the unsung hero of Futures, like the whole ability of, or they're the main component of actually tying all concurrent tasks together. So streams are definitely important. I don't know if we should focus too much on new language features. I think making sure that the current API works well with the current language features, works well, because there's, I think the big advantage now writing actually a lot of async await-based code with the new syntactical support is that you already have a number of patterns that people can just learn by typing that, and the program is really good at this. Before that, we were in the situation where pattern-based programming with Futures was hard because you would have to exactly know how you write, and basically the moment we had infiltrate and return position, you could write your own async functions, and understanding how you would write them and glue them together, and that you would have to avoid borrowing. There was a huge list of things that you would have to take care of, and you don't need that anymore. Error diagnostics are still a big problem that I think is much more important. Like these three pieces of API: read, write, stream, and then our reporting. I'm not that much into that.
Now, when it comes to streams, I know one of the concerns that's been raised is that the current stream definition, basically, it's kind of like iterator. You have to return ownership of each thing of each new element in the stream. And that's often not something you need to do. Like if you're just doing for each on streams and processing one element at a time, you don't necessarily need to own each element. You might rather borrow it from the stream, which would allow the stream to have some internal storage that it reuses over and over. And that's a similar, people want that for iterator too. It's often called streaming iterators, which adds a little confusion because I sort of prefer detached as like I give you ownership, attached, I hold on, doesn't matter. That's one of the concerns I've heard, and I'm not sure how to reconcile that. Like I think how to balance, I think we could make progress potentially on stream as it is today, but it's a longer road to get this other version because it requires generic associated types and we haven't even begun experimenting with it. I'm curious what you think about, like, do you think we should move forward with what we have? Imperfect though it may be, do you think we should wait? Do you think we should try to convince ourselves we have a migration strategy? What level of confidence? And is this a concern that you've seen come up?
I don't think it's, I don't see this as a blocker, to be honest. The problem that I see there, and also in a lot of discussions around the async read and async write traits, is trying to find the abstract trait that can be mangled into any specific use case. And I don't think that's very useful for the reason that you might end up with a generic thing that has tons of privileges on how it works externally. That's the first problem. And the other one being that you might end up in a situation where you may have, depending on the way you use this interface, there's certain methods that you should prefer to use and others not. For example, one of the discussions in the async read and async write discussion is, can we use async read and async write on top of completion-based and of readiness-based APIs? Can we find a trait definition that works with both? I don't think that's useful. I think on the level of actually writing an application, there's a mid-level of abstraction where you want to say, I do I/O in a certain kind of way, and I want to be abstract about it, but I don't want to be completely random about it. And especially if we're talking about API like IOUring or other kind of completion-based file system APIs, I think they're a good example. If you're using them, you're probably an expert user, and the way you want to deal with this, also for example in databases, is you actually don't want to compose everything out of futures. What you want to do is you want to have a larger operation that says, write 100 rows to disk and have a future around it and tell me when you're done. So I'm not a huge fan of, we need to end up in a world in which everything is composed out of futures. I'm far more interested in futures on the level of, I want parts of my application, parts of my system be able to have a generic way of signaling that they're done, but the blocks can actually be quite huge. My main criticism around a lot of these debates is the ability to cover all use cases, while from my mental model at least, I would put a streaming iterator or whatever the name of it is into a different bracket. It merits its own trait. And the same goes for a different kind of stream type. We can totally have two of them. And will also make it easier in the end for developers because they know what's at hand. One of the reasons why I think stream can actually be deprioritized a little is that in many of the applications that we see, it is also completely fine to actually just take a specific type, for example, TCP listener, or at a specific channel implementation, and work through it without a trait-based interface, but actually just through its raw API, without being abstract.
Yeah, I mean, well, one downside I see to that is interoperability is harder. Like if you want to have some generic library that takes a stream of data, does something to it, and generates a new stream or something, you can't really do that.
Library level, I agree. On a library level, I agree that it's a concern. On an application level, it's a classic case that libraries should be generic, but applications are concrete. So,
I mean, with Stream, what you mentioned, for example, syntax, syntactic support for streams, and that could be two things. That could be generating streams or consuming them. As far as I know, the only syntactic support for consuming them is like for await loops. By the way, are you hearing echo? I've been hearing echo this whole interview, but I hope it's not going to be on the recording. We'll find out.
I'm not hearing echo.
Okay. So, what I'm trying to ask is kind of, what do you envision people, like if we stabilized a stream trait with that alone, without any syntactic support or other such utilities, do you think that would be useful, and what would people do with it?
Yes, for the reason of components being allowed to be generic.
Okay, so primarily for people to write libraries.
Yes.
And if we added syntactic support, which kind of syntactic support do you think would be more important to emphasize, and why?
I would actually de-emphasize syntactic support altogether currently. That I'm not that big on what I call microeconomics. The current version of the for loop, which is basically for stream.next.await. If that's too long for me to type, I can put it on editor macro.
I think that's a reasonable answer.
Yeah. I think we made a huge stride towards making things usable, and it's very convenient to write currently. So I'm pretty good on that side.
Okay. Well, I'm kind of inclined to wrap it up soon, so I wonder if you have any parting or final thoughts or other things we haven't talked about that you wanted to talk about.
I think one of the things that were the reason why I would like to see more stabilization of those primitive parts is the thing I'm lacking is seeing patterns evolve, how people write abstract libraries over multiple executors, patterns around different kinds of classic problems, like for example, how do I stop a stream? So I'm reading I'm reading from multiple channels. How do I stop this operation? For example, because the service shutting down or because a client disconnects in a structured fashion and things like that. And these are all not language concerns, but I think the reason why those patterns don't evolve is because the languages or the base language, also in the sense of the primitive types for it, are still evolving. So it's pretty hard for people to grasp on how do I do this a little more high level concept X easily. How it gets hard with the base components are missing, or at least not stable. For example, one of the things that I believe, for example, the select macro is used for a lot of places is selection is pretty often used in places where there's a better name for the operation by actually just defining a type that has the proper name for the operation and constructing it. Being from object-oriented background. That's the way I work. So I'm not that big into super abstract operations that you can move into every direction. I'm more for, this is the thing I want to do, there's a type for it. And this is a subtly different thing that I want to do, there's a different type for it. And I can construct this, might be a future, and then I spawn that one.
Okay, I'm not sure what it would look like for those patterns to evolve. Like, can you, I mean.
Support libraries, for example. Any kinds of support libraries that make a little thing more easier, but are not, don't take part in the, so basically support libraries for writing your library instead of libraries like futures, which define an interface that everyone agrees upon. You can already see that a little bit with pin. There's a couple of pin utility libraries currently that make pin detections easier and safer and all of these kind of things. These kinds of libraries. Async-RS, for example, now has a library called stop token, which implements this stopping of reading from a stream as a type. Can say, okay, now stop this operation the moment the stop token triggers. These kinds of patterns. And
would async task fit in that definition? Is that the kind of pattern you're talking about, or too low level?
Async task would not fit into that definition. It fits in it by allowing people to write their own reactors and executors, or this whole component, while not having to write the really hard part of doing the task allocation proper. Because that's the dangerous and unsafe part. So it's good to have that as a library. So it kind of is on in a different way.
Yeah.
In the space below actually executing futures, what I was talking about more, basically support special kind of future implementations that, for example, execute different combinations of futures in a particular fashion.
I'm trying to figure out why that's different from what futures are. Like the futures crate is already doing. It seems like it's very similar, at least, to some of the things the futures crate offers.
Futures utils does a bit of that. For example, futures unordered is an example of such a type.
Okay.
So it's not that I see this as a widespread practice outside of this pretty constrained space, which is currently the futures crate.
Yeah.
So
and kind of it'll just to some extent it just takes time to develop those crates, but I guess and to recognize those patterns. But I guess having a standard trait like stream would kind of open up a new domain where you can do that. And with absent a standard trait, you can't really write the pattern in a generic way. I usually just call those combinators, I guess, although I think but
it's probably not the worst term for it.
Okay.
I'm not sure if every of the support crates would ship a combinator. But
right.
Yeah, it's good. That kind of thinking. So for example, there's currently also crates that tag futures for logging and all these kind of things. So there's a huge space of just practical things that we need to build, where I also don't see that I don't know if we're helping there, if we're iterating on the language too fast. I think it's I think how's it called? Calmer waters would help a little, and people actually writing all the practical things that are missing. Tracers, like there's the good tracing implementation and the tracing library, and bringing all those in a stable.
Yeah. I mean, so okay, so the big lessons I can take away from this conversation. You don't think we need any more language support? Like, for example, async function, I mean, that's for the short term. You don't, so like focusing on async functions and, well, focusing on syntactic sugar for sure, you don't think it's a good choice if we're on streams or something like that. But you do think it makes sense to signal that certain interfaces are stable, whether that be through a futures crate or whether it be through moving them to the standard library so that people can sort of start to build an ecosystem around them. And
Exactly.
Of those, read, write is top priority, stream would be somewhat secondary.
Yes.
I think you feel like it's better to have this. I'm sort of inferring here a little bit, but better to have something stable, and even if there are some outstanding concerns that might later down the road necessitate a second trait or just be there, just be suboptimal in some respect, than to wait forever essentially, or to delay too long.
Exactly. Also, you mentioned async functions and traits. I mean, we already have the problem that we don't have impl trait in traits. I think that's one of the cases where it would be nice if we had that. On the other hand, there's practice around that. Practice has formed, and I'm a huge fan of that language communities form practices around their language issues. And I think we can all agree that this is an issue. I don't think we need to rush on it because you wrote that nice blog post about all the subtle details of it and all the subtle problems around it. I don't have a feeling that rushing through that just for the sake of enabling that syntax helps, given that there's pretty standard practice around it. It's not nice, but
yeah. I think one thing I've thought about as a possible first step would be stabilizing basically focusing on impl trait, so impl trait in traits, at least certain cases of it. I think there's, as well as sort of type alias, like type foo equals impl trait, which lets you kind of define a type variable foo, or a type alias foo that you can use in various places. And then this would let you, in certain cases where you would use async functions in traits, you could sort of manually desugar them more effectively. So there might be, I guess what I'm saying is I think there might be room. I thought, well, if we're going to make progress on that feature, we have to start sort of fighting the Hydra. And I think we might consider doing that. But
I actually think that's a reasonable path because everything that's possible manually kind of works well for a certain time, and you can see that in a lot of languages. Java had manual ways to build certain kind of patterns for decades until they added syntax for it. So, for example, closures through anonymous classes. And
yes, I remember.
They had this for 15 years or something like that, to the point where in the end they added just IDE support for it. And it's never a beauty, but there's having spent a lot of time in actual application development, in the end, if it works, I don't care that much. If I have a pattern at hand where I don't have to think much and say, okay, so presented with this case, I need to do this, and this is the setting we're in with async in traits. We can have it's a lot of manual typing or code generation if I want to do that, and adding a macro or whatever, but I can do it. I can write traits that I can use in an async setting, and the ways to do that are not, there's not particularly many of them. So this is something we can live with for quite a while, and relax a little bit on that, I think.
Yeah, I think that's true.
Knowing that programmers are actually good at working on language warts.
Yeah, although I think that's true, but I also think that pursuing impl trait has value just as it's its own feature, which we need. So
again, like taking that gradual, like the way you presented it, actually thinking about infiltrating traits first and solving half of the problem
Right.
in the midterm, and then the full problem in, I don't know, 2 years or something like that, makes it more manageable.
I think the other feature that's on my mind is async closures, because one of the things that came up in another discussion was that a lot of the that when it came to the futures crate, there were a lot of combinators with APIs like filter and map and so forth that have a lot of choices, and that with lacking async closures as we do today, and certain features sort of steered you in one direction, but it might not be the direction you would ultimately want. I forget exactly the details, or I mean, I could go into it, but I don't think we have time or want to, but I think, I'm not sure what that argues for. I think the challenges around async closures are actually quite similar to some of the, like at least the way that I've had the Taylor presented it, sort of, you wind up needing GATs and other things. So I think we can't solve them in the near term. That might be an argument for like pushing for a few, basically leaning on the futures crate, first, or keeping things out of standard that might be affected by such a change. So I think examples would be adding convenience combinators to the future trait. Maybe we want those to live in an auxiliary crate for the time being. But I'm not sure.
I think that makes total sense.
Yeah.
I think that makes total sense. With a lot of the obvious previous example for that is the iterator trait in libstd, and the reason why we have that there in that form is, I think, also because it was designed at a different time. So I'm not sure if the practices of Rust 1.0 should be the practices of Rust 1.39. So
I mean, I'm pretty grateful I don't have to import iter tools every time I do anything non-trivial with an iterator.
That's correct.
On the other hand, it's not the worst problem ever for the short term, if you have to import. Okay.
I mean, so that's basically one thing that a lot of the base libraries now give you. So if you base your application on async-std or Tokyo, you basically go through their prelude and then you get that all. So basically by choosing the platform that you're basing your application on, you automatically get these. So you need to choose a library anyway. So currently there's no state in which you can do bare libstd development for async anyways. So for, at least from our view, our perfect world for async std-based applications is that you never need to import futures in an application, while in a library, you should always import futures because you should go through the futures interface and not through the std, async std interface for reasons of compatibility. That's kind of my current way of thinking. Some of futures doesn't fit into that thinking. So the third part of it is, if you want to use the futures utils, we make sure that we implement all of these features. We make sure that all futures utils can be used with the API that we provide. And that's kind of the that's kind of the thing where I still have a little bit of an issue in where to grab. If I think it's mainly a communication issue, because people still see futures as this whole block, while it's now separate crates, and each of those crates has a little bit of a different role. One of them, or some of them, being interfaces that people should use, and others being utilities on top of these interfaces. And the name gives it away, but I think that also gives us the ability to think about which one of these do we need to stabilize for the reason because they're compatibility crates, and which ones can we iterate on because whether I'm using futures util 03 or 04 doesn't change my application much.
Yeah, I think. So I just thought of another thing I wanted to ask you, but I don't know. You probably have to go soon. If you have a few extra minutes, there's another topic I wanted to ask. Let me think. Now you distracted me with this futures question. So, sorry, let me just take a note here. What I have two. So first of all, to finish up on the futures thing, I think it seems like a big part of that question is going to be just how can we dispel the confusion? Like, I think the current design is probably, not surprisingly, very well thought out, but maybe not very well communicated. And I don't know whether you should change it so that it's easier to communicate. That might be the case, or it might be that we just need to like have a great document that kind of the great readme.md or something that kind of lays out the role of the best practice for relying on the futures crate, depending on what you're doing. I worry a little bit that if it's too complicated, it's going to get us into trouble.
I think the first step would be to actually think about what the role of all of the crates is and note it down somewhere. And classic goal setting. And the second part is do more writing around especially these concerns. How do you use this library for this effect? How do you use that library for this effect? What is utils for? How do you use that properly? Maybe in the async book, because that's definitely the thing that people see as the reference documentation and the source of truth.
Yes. Which kind of brings me to the next question I wanted to get at. From your experience teaching folks and so on, one of my concerns around, or I think a huge problem that the Rust async system faces right now is basically just, where do I start? There's a lot of parts and you have to put them together in the right way. Some choices to make, like, most fundamentally, do I pick async-std? Do I pick Tokyo? Do I pick one of these other choices that are out there? I think those are the two most general purpose, but there might be others. But going from there, how do I use the futures crate? And I'm kind of wondering how best we should address this. I think one part of the answer might be a focus on, interoperability and generating things like, you remember the runtime, now deprecated, but the runtime crate that sort of let you bridge across many runtimes. That might have been a way to sort of remove some choice. We could imagine trying to do things like this global executor proposal that Boats brought forward. But I kind of have the feeling we're not quite there yet, and certainly not in the short term, we're not there. And maybe we can do things more from a documentation perspective. I'm not sure if you have thoughts on how to address some of that question.
I actually enjoy that choice.
I also think the choice is a great thing. I just think we need to help people make it a little bit. At least lay out the choices they have to make.
Yes, I don't like delayed choices. This is actually my my sometimes big disagreement with a lot of people from the Ruby world. I actually don't like the way Rails made choices, because Rails is basically, you generate a project and this is what you have, and these are all the components that you're going to use. You're going to use MySQL. You're going to use Active Record as the database access library, and in the short run, this is very good and productive. In the long run, it means that if you figure out after 3 years that Active Record was not a good choice for your specific kind of database interaction, you lost. And coming from a slightly different engineering background and actually being involved in a Rails competitor that took a very different route, where you pick and choose your components as the first step of starting a project, the big thing that was lacking in the Ruby community back then, and that's lacking us, is informing people out of all those choices. These are the things that are here. These are the goals that they have. And that also opens up, for example, one thing that I would love to see is, for example, a non-performance oriented executor that might do heavy tracing on this is what happens. This is what actually is currently happening in your API. Like, one of the basic questions that people currently have is, what's the difference between joining two futures and running them, and spawning two tasks and joining to wait on them? Let's say, for someone who has experience in that space, that's a pretty simple thing. But I think the biggest problem that we have in that space is that we have enabled people to safely work with concurrency. And the problem is, then you figure out that a lot of people are actually missing the language to even competently choose those libraries. So even making them aware that both Tokyo and async-std exist, then we're in the problem of, if you lack the skill of comparing them or exactly knowing what the primitives are that you're talking about, then you're lost there already. So from a teaching perspective, there's the much bigger problem that education around concurrency is hard, especially on the level that Rust works on, because it used to be the privilege of the V8 implementers to actually build these libraries, for example, and then there's JavaScript and you just interact with it. So yeah, that's
yeah,
but
I'm not really sure what
in general the choice is good.
Yeah, I strongly agree with that. I think, all right, very good. Choice is good. I think I know what, I think we can kind of end it on that. We talked about the major priorities. I'm just looking back over my notes here about syntactic support, about a focus on stabilization, what language features there might be. All right, well, thank you very much. Sorry, this has turned out to be quite long, but pretty interesting.
It was enjoyable. Thank you.
All right, talk to you later, Florian.